Welcome to Lecture 1. This lecture is called The Learning Problem. In this lecture, we will define what is machine learning. And we'll also talk about the various applications of the machine learning. And finally, we talk about the components of machine learning. So let's talk about some skills that you can say I have acquired. As humans, we learn a lot of new skills. As a baby, one of the important skills is how to walk, how to learn, to communicate, how to learn a new language. Or we can also think about learning the first time that we learned how to ride a bicycle or driving a car. In all those scenarios, we had some kind of observations, and we used all those observations to acquire skill, usually with experience. Learning how to walk involves falling down many times, strengthening the motor neurons in your brain, and learning from experience. Learning a new language involves a lot of observations coming from a textbook, a dictionary, any other source of information. For instance, learning, let's say, a programming language, C, C++, or Java, also requires seeing, observing a lot of information from the text, from the video materials, or all the observations that you have seen while performing a programming assignment. And the learning process involves making a lot of mistakes, trials and errors. And all those are biologically related to building some kind of neural networks in your brain. So, again, the important thing in human learning is we need to have some observations and then the process of learning. And at the end, we have some kind of a new skill. We can also put the machine learning as acquiring skill, similar to human learning, with experience accumulated or computed from data. So instead of observations here, we're talking about the data. And also data is somehow related to observation. So in the case of machine learning, data can be the images, the videos, the sound, data, or text, or any kind of quantifiable data that has some structure that we can observe. And similar to human learning, here we have machine learning. So machine learns from the data through experience and acquires a skill. So now let's talk about what is skill. So we can describe skill as improving some performance measure at some specific tasks. So in machine learning case, improving some performance measure with experience computed from data. So the performance measure is computed from data. So we have some data, machine learning learns from these, and we have some improved performance measure. So one of the examples of the machine learning is in computational finance. So for instance, we have a stock market and then data acquired from the stock market. And then we want to train a machine learning algorithm to learn from it so that we have more investment gain. Now, imagine improving performance measure as a human. So you acquire some skill. For instance, you can say, I'm a very expert level programmer in, for instance, C++. So how can we describe performance measure associated with your skill in coding? You may wonder, why do we use machine learning? Why we care about improving performance measure? Why do we need data? Is machine learning useful? To answer that question, let's take a look at one possible application of machine learning. Well, we want to build a tree recognition system that takes input of images and then tries to recognize whether this is the image contains tree or not. So there are three possible cases. For instance, in the first case, we can define trees and hand program. This is a very difficult task. In contrast, let's try to teach a 3-year-old child. Surprisingly, this child can learn to recognize the tree from images very fast. So it's enough to show a child a few images, even one image of a tree, and say, this is tree. So that the human can also learn from this visual observation and then learn whether the image contains tree or not. In machine learning case, so we can also use data to learn from it and then build a tree recognition system. In this case, it will be much easier, faster to build a machine learning based tree recognition system than the handcrafted or hand programmed. Uh, so, why do we need machine learning? Machine learning allows us to build complicated systems just using the data and can be much faster, easier to build. Again, so we can build these kind of true recognition systems using a traditional coding, hand program, which may involve thousands of lines of the code where we can define the tree structure or the branch, how it looks like. And in contrast, machine learning may require just few lines of the code and few images of the data that we can learn from. So machine learning can be much faster, more efficient to build than hand-programmed software solutions. So the machine learning provides us alternative and much easier ways to build complicated systems. Some of the use scenarios are listed here. So for instance, when as a human we cannot program the system manually, for instance, on navigating Mars, when human cannot define the solution easily, for instance, in speech visual recognition task. So it's very hard to hand program speech recognition systems or visual image recognition systems, or when needing rapid decisions that humans cannot do in the order of a few milliseconds. So in high frequency trading, in let's say high stock market application, or when needing to be user oriented in a massive scale, consumer targeted market. So you can think of Amazon shopping. So Amazon also uses a machine learning algorithm to come up with a customized recommended items for you based on your past experience of shopping. These are only few examples of machine learning. Nowadays, machine learning are everywhere. Let's go through some key essence of machine learning. We defined machine learning as improving some performance measure with experience computed from data. So there are three important things here. So first is the data, right? And then we want to improve performance measure, which is computed from the data. So we have data, machine learning algorithms learns from data and eventually improves some performance measure. We can use three criterias, let's say, to decide whether we need or we can use machine learning at a task that we want to solve. For instance, the first criteria is given we have data, right? And then that data should have some underlying pattern to be learned, right? So we should have some repetitive, some structure in the data that machine learning can learn to improve performance. So our data should not have any randomness. There should be some underlying pattern, some structure in the data. Second, we can use machine learning only if we cannot solve that specific task using few lines of code. If you can solve that specific problem that you want to use machine learning using few hundreds lines of code, maybe it's better to use programming approach. In the previous slide, we talked about the tree recognition problem, whether it was not an easy solution to hand program system. Third, somehow there should be enough data, okay, about the pattern. We should have enough amount of data so that we can use machine learning to improve some performance measure. So these three key essence will guide you to decide whether you can use or you want to use machine learning at some task. Following, let's take a look at this short quiz to understand the usefulness of machine learning. Which of the following is best suited for machine learning? So first, imagine, so predicting whether the next cry of the baby girl happens at an even numbered minute or not. Can we use in this application, this specific case? Second, determining whether a given graph contains a cycle. Or deciding whether to approve credit card to some customer. Guessing whether the Earth will be destroyed by the misuse of nuclear power in the next 10 years. Which, again, of the following is best suited for machine learning? Can we use machine learning in this case? Or this one? Or 4? So just take a moment and then think about the answers. All right, here we go. So in the first case, the babies are so unpredictable, right? They cry randomly. It's very hard to predict whether they cry at even numbered minute or not. So in this specific case, we cannot use machine learning because there doesn't exist any pattern to learn, right? If those babies had some, structure, some pattern of crying at some even number or minute, then we could. But in this case, it's very hard. So we cannot use machine learning in this specific case, even if you want to. Because, yeah, we can, but the performance measure will be very, very horrible. So second, determining whether a given graph contains a cycle. So in this case, probably the better solution would be just hand program. Maybe just few lines of the code, you can determine that whether you have a graph, whether it contains a cycle. So in third case, deciding whether to approve credit card to some customer. So here we have yes. The answer is we can use machine learning in this case. So we have the pattern, the customer behavior, and the definition is not easily programmable because we have thousands of other customers and then each customer behaves differently. So hand programming would not be that easy. And we also have data. So each customer have some data related to past use of the credit cards or loan and some bank operations. So we have pattern. The task is not easy to solve with programming, and we have data. And okay, this is the best answer, the best use case of machine learning. And then The fourth case, let's take a look. So, guessing whether the Earth will be destroyed by the misuse of nuclear power in the next 10 years. Well, arguably no, because we don't have data yet, right? So, in this case, we don't have data. If you had experienced the Earth being destroyed several times, if you had enough data, then probably yes, but we don't have data in this case. So, machine learning would not be possible to use in this case. Whenever we have data with existing underlying patterns, we can apply machine learning to solve some problems of interest. For instance, the following are only limited examples of the application of machine learning in food, so related to finding and searching a restaurant. So we can collect the data from people's Twitter data where they share about their feedback about the restaurants they have visited, the locations, and the reviews, and we can train a machine learning algorithm to tell food poisoning likeliness of restaurant properly or in closing application. So we have data that represents sales figures plus client surveys, and we can train these algorithms to give good fashion recommendation to client, right? Or in housing. So we have data again characterizing the building and their energy load. We can train again a machine learning algorithm to predict energy load of other buildings closely, right? Or transportation. So we have data, for instance, some traffic signs, image, and meanings, and we can train again machine learning to acquire skill to recognize traffic signs accurate. In simple words, machine learning is everywhere nowadays. One of the interesting applications of machine learning is in education. Let's take a look at this example. So we have data that corresponds students' solution records on quizzes on a math tutoring system that is collected there. And then we want to train a machine learning algorithm to gain skill that predicts whether a student can give correct answer to another quiz question. Another quiz question which has not been seen by the student. So one possible solution for this problem is to collect data from this math tutoring system. For instance, 9 million records from 3,000 students, and then train a machine learning algorithm that will automatically determine the strengths of student and then difficulty of the quiz. So basically, machine learning learns from these huge amount of data whether a student, okay, one of the student among 3,000 is able to provide correct solution to new type of quiz. The other widespread application of machine learning is in entertainment. We have websites like Netflix where you can watch movie and leave your feedback whether you liked it or not. So we can collect data, how many users have rated some movies. And then we may want to build a machine learning system to predict how a user would rate an unrated movie. Of course, the main task here would be to recommend a movie to a user so that he would leave a very good positive feedback and who would love the movie. One of the earliest competition held by Netflix was in 2006. This was $1 million prize competition. In this competition, Netflix provided data that amounts like 100 million ratings that from for almost half a million users to 17,770 movies. This is the data provided by Netflix. And the skill was to train or come up with a machine learning algorithm that would improve their recommender system by 10%. And then the price for this improvement was $1 million, which actually was held. There are many similar competitions held in early times by Yahoo, for instance, or KDD Cop, or even nowadays you can find so many competitions on Kaggle, so-called Kaggle website or platform. So, for instance, you have ratings from a lot of users depending on the songs, and then machine learning tries to learn our preference and then recommend a movie or song which we will like. One of the possible machine learning solution for such recommender system again would be based on viewer and then movie factors, right? So for instance, here we have some viewer with previous existing reviews of previously watched movies. So this viewer likes comedies less than action. He likes more like action, prefers blockbuster, and whether he likes Tom Cruise in the movie or not, and many other characteristics. So we have all this information for this user, right? And the task is to recommend a movie that will make the reviewer happy. So he would like the new movie. And then Netflix will try to train a machine learning algorithm that will match these contents, these factors. Well, whether he likes comedy, okay, the movie has bigger comedy content, probably he would not like it. So the task is to train algorithm, okay, to learn from the previous entries of the viewers and recommend a new movie accordingly. So learning represents we have known ratings, we have to learn factors, okay, these factors hidden, and for unknown rating prediction. All right, so the following question, which of the following field cannot use machine learning? So cannot use, right? Cannot use. Finance, medicine, law, none of the above. Take a moment, think about it. Which answer is correct? All right, so we see none of the above. So that means we can use machine learning in all of the cases. So first, finance means predicting stock price from data. We have data collected in finance from stock price, stock market. Second could be in medicine, predict medicine effect from data. So data could represent any collectible data, images, any gene-related data. Law, summarize legal documents from data. So these are again a very few limited application of machine learning. Machine learning are ubiquitous. They're everywhere nowadays. So far, we talked about machine learning, the definition of machine learning, and its application. Now, in this part of this lecture, I will go through the the components of machine learning using a metaphor problem related to credit card approval, right? So for instance, imagine you apply for a credit card and then you go to bank and then the bank will ask some information about you. So some of the information can be related to age, how old you are, gender, okay, annual salary, year in residence, okay, 1 year, year in job, current debt. All right, these are just very few information bank uses whether, okay, to decide whether to approve your credit or not. So here's the task is to come up with a machine learning solution that would approve credit card or deny credit card for this applicant. So we have some unknown pattern that needs to be learned. So let's formalize the learning problem with some basic mathematical notations. We represent input or the data as x. Okay, x is in this specific case is a tall vector. Each entry is corresponding to one feature of customer application. Okay, now a metaphorical example. We have also output that needs to be learned or estimated. In credit card approval case, this will be a good applicant or bad applicant. This could also be a approved credit, denied credit. So we have X and then Y, input and then tentative output. And the main function that needs to be learned, or the main pattern, unknown pattern that needs to be learned, we call it as a target function. And we denote it as F. So F takes X and provides us with the answer, approve or deny. And we can also imagine, think of this as ideal credit approval formula, which we don't know. Okay, so this is the ideal formula and our target function, but we don't know about it yet. So it's unknown pattern that needs to be learned from the data. And we represent data as D, denoted as a D. And D is a set containing X and Y, right? So customer one, the subscript represents first customer, second, N. So each customer may have a good or a bad indicator. This is output, right? So input, potentially tentative output, or some predefined output. So we call it as a D, and sometimes we use training examples because we train machine learning from these examples of the data from N applicants. Now let's define the hypothesis. Hypothesis, another function of skill, okay, that needs to be learned with hopefully good performance. And let's denote it as G. G also takes X and provides output Y. Well, and then G will represent the learned formula from the data. So the main difference between F and G is F remains unknown, and then this will be our target function, which we will never know, but we'll hope to approximate using other functions, for instance, the G. So we have this data set, X and Y, okay, generate from unknown pattern target function, right? So using machine learning, we will try to approximate this function or get another hypothesis G that will approximate our target function. We define the learning flow for credit card, credit approval example at the following flowchart. Our target function, unknown target function, is defined here. Let me remind you, the target function is the ideal credit approval formula, which we don't know. We also have these training examples, D, okay, with the X and Y. So X here is a vector or matrix. Y is a scalar. The Y could represent a binary value, good or bad, approve or deny. X here could represent the features or the attributes of the applicant one. We have N examples that can also correspond to N applications or the historical records in the bank. And we put a learning algorithm here in our flowchart. A learning algorithm, we call it A, will learn from the data and get us some final hypothesis. So we defined G, as our final hypothesis that will be learned from data. And we hope that it will approximate the target function f. So what we have, in summary, we have target function unknown. This is ideal formula. And we know that there is no programmable definition, otherwise we wouldn't have used machine learning. Second, so we have a learning algorithm that selects us a hypothesis G with the hope that it approximates F. And G can be different from F. Okay. So what does the G look like? Where do we get them? How do we get started with the G? So F is unknown. Well, G, what about G? So to answer that, we define a hypothesis set called H in our flowchart. So training example, learning algorithm, and then hypothesis set. So imagine this is just a big set of functions or the formulas, right, that contains different versions of G. So what learning algorithms are? Okay, takes input and then takes one of the functions and then tries, okay, if with good performance measure, we can declare it as a G and then hope that it approximates F. So let's assume one example. So assume that G, okay, our final G, expected G, is a member of this set, right? That is, one of these functions is our actual G. So in other words, approving credit if, let's compare three candidate formulas, H1, H2, H3. H1 approves credit if the annual salary is higher than 80K. It's one, okay. H2, okay, if debt is higher than 10K. Really? Would you approve that? Would you use that function as a G? Or H3, year in job, less than 2 years. Really? Okay. So anyway, this H could consist thousands or millions of functions or candidate formulas, which the learning algorithm picks one which, provides us very good performance according to some measurement or some criteria, and then declares as a G. And we hope that G will approximate our unknown target function. So this set, again, could be millions of different functions or even less set of functions and can contain good or bad hypotheses. It is up to algorithm to select the best one and then declare it as a G. And also, let me just clarify the learning. When we talk about the learning model in machine learning a lot. So the learning model represents hypothesis set that you define plus a learning algorithm. Okay, so hypothesis set, this H1, H2 can take any different function. Right? This can be class of linear functions, nonlinear, polynomial functions, or probabilistic functions, or different set of functions. It's up to the machine learning engineer to decide. And learning algorithms. These are the two things that you need to decide as a machine learning engineer. Data is given, okay, your task is clear. Here, depending on the type of the hypothesis functions and learning model, you can say, okay, my learning model belongs to a class of neural networks. By putting every component that we discussed into one big flowchart, we can define this practical definition of machine learning. Well, again, we have unknown target function that needs to be learned. This is a ideal credit approval formula, but we don't know. What we only have is training examples, training data, okay, historical record in the bank, and our learning model. It's learning algorithm plus hypothesis set that we define is our learning model. And the final, and then the only one of the important goal is to find the G in the given hypothesis set H that will close approximate our unknown function f, right? So this approximation is another topic that we need to discuss. How can we make sure that the one of the G selected by learning algorithm will approximate target function f? Here, let's just first define the definition of machine learning. So in machine learning, we use data set to compute hypothesis G, okay? That approximates our target function f. Here we have another example of quiz, of fun. Based on the previous information we have learned, let's try to form four sets. So the question is how to use the four sets below to form a learning problem for song recommendation. So S1 is the number of songs from 0 to 100. S2 is all possible pairs, user ID and song ID. S3 is all formula that multiplies user factors and song and factors indexed by all possible combination of such factors. And S4 is million pairs of user ID, song ID, right? So your task is to define which one of them is your X, Y, okay, H, or D. So the answer would be 2, second. So S1 corresponds to 10, 100 different types of the songs. S2, all possible pairs. So this will be our data X. S3 is all formula, the big set H, and then D is the pair of user ID and song ID plus rating. Okay, so we can see that S4 algorithm, okay, takes on S4 data, tries to estimate on H, and then we want to select G using our input as to get S1. To briefly summarize today's lecture, we have defined the learning problem and we discussed about what is machine learning, and we define it as we use data to approximate our target function. We have also seen some limited applications of machine learning. However, they are everywhere, and we discuss different components of machine learning.